In our previous video, we looked at free energy and we drew a comparison between free energy and the standard free energy. Okay, we said that standard free energy was describing the free energy of a process under standard conditions. So we said, for example, solutions were all 1 molar in concentration, gases were at 1 atmosphere of pressure, things like that. And we said that delta G was just going to be under non-standard conditions. But what we did not do was look at the relationship between the two of these. Okay. It turns out that we can write an expression here that is going to directly relate the free energy under non-standard conditions to the free energy under standard conditions. Okay, so the free energy under non-standard conditions is going to be equal to the standard free energy plus this correction factor, which is RT times the natural log of Q. Okay, so R is our gas constant. And because we're talking about energy here, we're going to use the version that is 8.3145 joules per mole Kelvin. T, as usual, is our temperature in Kelvin. Okay, and Q is our reaction quotient. Okay, you'll remember we talked about reaction quotients when we were discussing equilibrium systems. We said that the reaction quotient was more or less calculated exactly the same as the equilibrium constant, except it was done with non-equilibrium concentrations. So, for example, if we had a reaction that was some compound A being converted to some compound B, okay, the reaction quotient would be equal to the concentration of B raised to the power of its coefficient, okay, under non-equilibrium conditions, divided by the concentration of A raised to the power of its coefficient under non-equilibrium conditions. Whereas K would be calculated almost exactly the same, except the equilibrium conditions would be in place. Okay, so that's the difference between the two of those. Calculated the same way, just describing two different positions of the system. Okay, so what we're going to be able to do here is predict the actual spontaneity of a reaction under non-standard conditions by using data that we collect from the appendix at the end of our book that has all the free energies of formation. Another very important application of this, though, is the relationship between delta G and the equilibrium constant itself. If you think about it, we've already said that when delta G is equal to 0, then we are at equilibrium. Okay, we can also say that at equilibrium, that K is equal to the reaction quotient. So what we can do here now is plug these values into our equation up here and rewrite the expression. And we get 0 is equal to the standard free energy change plus RT times the natural log of the equilibrium constant. And then we can rearrange this a little bit further, and we find that we can directly relate the free energy that we can actually calculate from a table to the value of the equilibrium constant. Just forgot a natural log there. Okay, which means that if we know the value that we calculate from the back of the textbook, we can predict what the equilibrium constant for a reaction is going to be. Okay, all we need to know is what the temperature is and what the free energies of formation are of the individual compounds involved in the reaction. we can also see here how delta G under standard conditions really does give us more information about the equilibrium position than it does about spontaneity. Okay, we're at equilibrium, so we know the reaction's not really going to go anywhere in terms of moving towards reactants or products. But by looking at the value of delta G, we can see here that there's going to be three possibilities. Okay, we can either have a delta G that is negative, 0, or it could be positive. Okay, now if we look over at our values, what the value of K would have to be in order for these to be true, well, we see that we have a negative sign in front of the expression for RT ln K. Okay, so the only way that delta G can be negative then is if the natural log of K is a positive value. Because we know that temperature is always going to be positive, R is going to be positive. Okay, so the only way that the delta G can be equal to 0 is if the natural log of K is equal to 0. And the only way that delta G can be equal to a positive number is if the natural log of K is equal to a negative number. Okay, therefore, the value of K can be deduced as well. So to have a natural log of K to be positive, K has to be greater than 1. Okay, in order for the natural log of K to be 0, K has to be equal to 1. And for K to be negative, K would have to be less than 1. Okay, so what we see here then is that when we have a negative value for delta G under standard conditions, we're in a situation where the products are going to be favored. Okay, and if we have a delta G under standard conditions that is equal to a positive value, because K is less than 1, then the reactants must be favored. And then for K to be equal to 1, the products and reactants must be equally favored. Okay, so again, this is some very important information that we can pull about a reaction just by looking at table values at the back of our textbook.